Thank you very much. Can you hear me? Can you hear me?
Yes, sir.
Right. Okay. So my name is Nicolas Larrosa. I'm an associate professor at the University of Bristol, and I also have very strong links with a company called FAD in the north of Spain, which I did a few secondments. And I did a relatively good job because they're funding quite a lot of areas at time. So the method that I'm presenting is in this case is for trying to think about how can we do better fracture assessments, fracture avoidance exercises, and as an alternative method to the typical FAD assessment method and the crack driving force approaches. So I'm going to present. I want to motivate the work and then the presentation. I will show you the UFC concept. I will validate the method with experimental data, both from literature and from R6 data, and I will give you some final remarks. So in essence, these are the two approaches I'm talking about. This is so there's no way to point there, but so the upper graph is the FAD. You will, for those who are familiar, I'm sorry for the repetition, but you have a load dependent parameter in X axis and a fracture dependent parameter in the Y axis, where you have basically you've got increase the load, you basically reduce the fracture capacity, and that's because you have yielding or plasticity ahead of the crack tip. The nice thing about this one is that you plot your assessment point and you find easily understand where you are in terms of safety margins. The bad thing, or what I do not like about this method, is that you have crack size, geometry dependent parameters, material properties, and load in both parameters. So, when you change one parameter, both the assessment point moves in both directions. The crack driving force method is a different approach, although they both should yield to the same result. But you do a J elastic or a CTOD analysis if you're doing experiments or numerically, and then you see how the J value evolves with load. And at some point, if you're doing an initiation toughness analysis, you will reach the material property. So the assessment has two separate steps where you do your driving force assessment and then you value your driving force with your material resistance. So in essence, both methods are very well established. The FAD is in R6, it's an API by 79, it's used in DSM and I10. SynTAP and FitNet approaches also use the FAD, but in my opinion, there's still some room for improvement. And you have some of the disadvantages that I see here. In essence, there's some steps you need to do. You need to characterize your material properties, basically toughness, yield strength. You need to measure the crack size, an aspect ratio to have some sort of an idea of how would that influence your load bearing capacity. Also the loading mode and the system of loads is important. But there's also a need to understand how influence what is the impact of residual stresses on load bearing capacity. So there is a systematic approach, and in both methods you need the same kind of loads. Primary, there are mechanical loads. Secondly, there are residual stresses or thermal load, thermal stresses. You need to characterize the crack. You need to size the crack. You need to see where it's located. You need to determine your limit load or your reference stress, your ligament yielding, secondary stresses, so on and so forth. But both require kind of the same approach and expertise as well. So these are two examples for critical load analysis. This is covered in this book I mentioned at the bottom of my slide. Critical load and critical crack size analysis. You can do with both, and both yield similar results. But what if I say that we can get rid of these three states? Because we no longer need a reference stress. We no longer need to calculate or determine the ligament yielding, and we no longer need to assess the residual stress effects. You would probably say, yeah, how come? How would you do that? Well, I developed, together with my colleagues, a method called the universal failure curve, in which we propose a more intuitive and straightforward, what we call safety targeting approach for designing research. Basically, what we've done is we give it another spin to the wheel. So it's not a breakthrough, but it's just another spin to the way in which we understand failure. So if we start from the definition of KR in the FAD approach, it's very simple, but it does include all the necessary parameters. You have the stress intensity factor due to primary loading, the stress intensity factor secondary loading. You have a parameter called P, which is the interaction factor, which is a function of load. So for very low loads, residual stresses have a huge impact on our structure or low bearing capacity. For higher loads, tough material typically they wash out and have some sort of relaxation. So that value of P accounts for that. If we rewrite the primary loading and the primary stress and the secondary stress in terms of non-dimensional factors and yield stress, we can write KR in that way on the right-hand side, and at failure, we can work out what is the contribution of both stress levels to the failure regime, right? So in essence, what we have here is a primary load parameter, normalized one. We have a parameter with a chemical. We have the secondary stresses. Yeah. Nothing groundbreaking, but it's a different way of writing things. Okay. And these are the definition of lambda, critical, and k hat. So k hat is a function of the material properties, k mat sigma y, configuration factor, which is y, and the crack size. And this is just, and lambda is just the global stress, membrane bending, whatever stress you have, mixed mode bending, a mixed mode stress over the yield stress. So to validate this, we conducted a range of FAD assessments using signal effect test, which basically replicates NPF as an to perform almost 600,000 cases for a range of different pipe geometries, crack orientation, crack fluidable extent, aspect ratios, material properties, and residual stress, membrane residual stress. So one of the assumptions here is that the residual stresses are not short range and certainly breaking are members. A limitation of the methodology, but we can live with it and further extend it to make it self-accurate. So if we write the equation that I presented in the previous slide, this is kind of the same thing. It's a one-to-one. I'm basically having the same terms in both regions, so it's not giving a lot of insight, but it's actually quite reassuring. There are almost 600 points, but from an instruction integrity viewpoint, doesn't really give me much. But what if I remove FLR from that, and I remove V delta from the equation, and I just plot lambda versus k hat? This is what I get. So I get residual stress dependent curves, which give me the normalized load as a function of the configuration of. Okay? And this is quite powerful because we no longer need, and all results for a given residual stress level collapse almost in a single curve. Almost. I will show you some data about the scattering data. But you can see that from 0 to 100, actually delta should be 1. So that gives you some sort of a good insight of how the material would behave. So as you increase your toughness, you go from elastic. In this case, we model an LR value very high, but that's now plastic collapse. So elastic and elastoplastic behavior, right? So we have an elastic regime in green there. So I have three curves here. See them? Curves. The green square over there shows the elastic regime for 0, 40%, and 100% of the residual stresses. And in the elastic regime, lambda scales linearly with k hat. which is quite intuitive. You can see that, there is an effect of residual stresses on low bearing capacity. So the curves are moving to the right. And the spreading data in this region is very, very small. If you think about the FAD, for changes in LR, failure criterion is basically the same. LR is equal to 1. So there's changes in LR. This is where there is no significant effect of not considering the reference stress. So I capped the curves at lambda equal to 1. That's pretty much for the cycles. If you don't want to see the only. For certain type formulas, you might purposely want to higher those or strain hardening, let's say. Oh, the other way around. So that regime is the plastic lamp regime. So there is a minimum K hat toughness of which you will avoid any fracture mechanism and its plastic lamps. Yeah, and that will depend on your strain handling behavior. Okay? Or if you assume elastic perfectly plastic material, that would be a 1. And this transition regime will give you the elastic plastic. So you actually cover the 3 main regimes that you have in the FAD as well. As you can see, the spreading data in the elastic plastic regime is relatively high, but the highest spread in data is in the plastic lap, for which we don't really care because actually we're yeah. So what we actually care is how the curve looks in the elastic and the elastic. So the coefficient of variation is between the highest one is in the plastic glass regime and is about 5%, but in the relevant region for application is below 2%. And there's a lot of insight here from a mechanistic aspect that I will not go into because I don't have time. So we fitted a few equations. We have lower bound values. So these are our upper and lower bounds. We are going to use lower bound values for our assessments. And these are the universal failure curves that we are proposing. Okay? So for validation, one thing I want to show you is that we clearly capture the effect of residual stresses and how residual stresses are washed out as you increase your problem. So for tougher materials, residual stresses have a less severe effect on the lower capacity. Yeah? Right, so validation. So there's a seminal paper by Downlin and Townley that remember those who are fracture mechanics geeks. So they presented lots of pressure vessel data, burst pressure tests, for which they proposed a two parameter or 2 criteria approach. And I did plot those results into an FAD, and also I plotted into the UFC, showing that the UFC is a bit more conservative, but provides good estimates of the low bearing capacity. This is the first set of validation. Then one of my students went to the literature and said, bring every data we've got, even if it's not a pressure vessel, bring it so we can see how it works. So we've got here pipeline steels, burst pressure of pipeline steel. We've got bending of elbows and pipes. We've got CT specimens, fracture toughness CT specimens in aluminum alloys in different directions. We have PMMA, that's a polymer, fracture toughness. We've got pressure vessel steel, pipeline steel again. We've got PVC and a range of different materials. So as you can see, there was no report of residual stresses, so I assume there were no residual stresses in that case. But as you can see, the behavior is relatively well capped. Yeah, and you can definitely use this approach to try to estimate the low bearing capacity in a global sense. This is a normalized pressure. And the last one, which is the one I'm really interested in, is R6 fortunately presented cases where you have constant residual stresses in place, and they did fracture tests for constant residual stress levels and different, and that was very valuable for my validation case, because that allowed me to include cases with no residual stresses, the black dots, and then you've got 23rd delta, what I would call delta is 0.23, and we'll compare to the 20% one. then they've got 47 compared to the 40, 60, 50 something, and so on. So as you can see, the approach is quite good in predicting the load bearing capacity and when failure is going to happen, even when residual stresses. Yeah. So this is for two different aluminum steels. This is in R6. If you have R6, you can actually have a look at the raw data. We are going to publish a paper soon. Always worry a bit tricky with how I write things. 2 points only does not really go into in the right zone, but it's to be considered that the residual stress level reported is higher than the curve. So probably if I interpolate the curves, that will look better. Final remarks. We have a method after doing a lot of simulations with FAD. We have a method that allows us to estimate the critical pressure or the critical stress, whatever that stress is, as a function of material properties and configuration. We have decoupled load from configuration and material properties. And that's, in my opinion, really powerful because that not only gives you the freedom to move the point in the configuration material axis, but also links design and assessment to the same frame. We no longer need to calculate the reference stress, which is kind of a nightmare unless you have a software. And residual stresses are explicitly included in the methodology. Of course, there's further validation required, there's further work needed, but this is the first step. Thank you.